In this video, we're going to talk about the sampling distribution for a sample proportion. So this ties very closely to what we learned at the end of part 5. If we were talking about X, which is the number of successes in our sample, right, our binomial experiments, so our number of successes in a sample. Well, we had two ways of thinking about that. X could follow a binomial distribution, right? That was the true distribution it followed, with N trials or sample size, and P probability of success. And we also knew that if our sample size was big enough, we could approximate that using a normal distribution, which was centered at NP with a standard deviation of the square root of NPQ. So that's what we covered before. What we're talking about now is not the sampling distribution of the number of successes in our sample, but the sampling distribution of the proportion of successes in our sample. So now what we're talking about is this P hat. This is our sample proportion. We find this proportion by simply taking the number of successes that we had in our sample and dividing them by the total number of trials. So this formula here is very important. In fact, this is like similar to our IQR formula, Q3 minus Q1, or our residual formula, E is equal to Y minus Y hat. It's one of those ones that is not on the formula sheet, but it is kind of crucial and at the center of a lot of things. So you definitely want to have this memorized. And it totally makes sense. If you want to find the proportion of successes, just look, see how many successes were there over how many total trials. And then we still denote P. Before this was our probability of success, but that's same thing as the proportion of successes. And when we're talking about probability of success, that was the true probability. And now we're talking about our true proportion of successes, or the population proportion of successes. So the first thing we have here is a classroom experiment. This is similar to what we will have done in class on Tuesday. And I'm going to just kind of ignore this for a second and bring up the simulation that we actually used before when we were talking about the number of successes. So remember when we were in StatCrunch previously, we looked at coin flipping and we simulated a coin flip. I think we did it, I don't know how many we did it for, but let's go ahead and just say, let's do this for 100 things. So we're going to simulate 100 tosses of a coin with a probability of heads of 0.5. So a fair coin, 50% heads. And remember when we did this previously, we could sit there and run this for 5 runs and it would pop out the actual different number of heads that we saw. And then we could say, that's a little slow, let's do it for 100, 1,000, do it for another 1,000. And that's when we started to see that approximate normal curve. But we don't want to look at numbers. We want to look at proportions, right? We want to take those numbers and divide them by our overall sample size. And hopefully, we can kind of immediately see how this would happen. I'm trying to find my little drawing thing. Sorry, guys. I'm being slow. So in this case, right, we can kind of see how this would change. If we were just going to take our P hat and calculate it as X over N, right? Down here at the bottom, we have our X's, the number of heads that we received. And we know we chose to make this something where N was 100, right? Flipping 100 coins. So we could easily change this. All we need to do is take each of these bottom numbers and divide them by 100. So instead of my distribution being centered at 50, my distribution would be centered at 0.5, exactly the proportion we would have expected. So let's go ahead and redo this with that in mind. So if I come back here into my options, I actually could choose to tally the heads either with the number or proportion. So I'm going to change this to proportion and play this game again. So if we're going to flip 100 coins with a probability of heads of 0.5, we do that 5 times. You can see, kind of see what we had before. Somewhere around 0.5 is where our actual value should fall. And then we could do this 1,000 more times, 1,000 more times. And you can see we are always going to be centered at about 50% or 0.5 because that's what our true probability of heads is. So that is what we're looking at. Now, what really matters here is how our spread changes, how our variance changes. The mean, I think, seems pretty straightforward as to why it's 0.5. But if you look back at our lecture notes, I want you to see in these 2 examples, in one of the examples, we are using 10 flips of the coin. The other, we're using 20 flips of the coin. This capital N here is the number of replications. That's me pressing that 1,000-time button. So this is 200 times that they flipped a coin 10 times. You can see both of these are centered where we expected, 0.5. But what's the big difference in terms of their spread? So they're both centered at 0.5. We can see here when there was only 10, oh no, when there was only 10, it was possible to get out here at 0.2 and even 0.9. In order to get 0.9, this was 9 out of 10 coming up heads, right? And this is 2 out of 10 coming up heads. So we can kind of see exactly where all these values are. Here, we do have 1 in here, but we have 1 time. It looks like that is about 1 tall where we got 9 out of 10, maybe heads. Versus here, or I guess this is really 8 out of 10 because of the fact that we only include the first one. But this happened 10 times, whereas here, it only happened between these two probably 3 times. It's a little less likely. Most of our data is more centered towards the middle of this distribution. So let's kind of keep that in mind. So as n increases, we'll have less spread. Let's see how that looks on our little simulation. So let's keep in mind when we're here, it looks like we're about 0.35, yeah, to 0.65 about. You could even click on these and feel out, okay, that's a 0.67 was our highest one. So we can actually see where these are. If I go back to my options, what we just said is that if we increase our sample size, we should get less spread out. It should be harder and harder to get away from 50%. We actually talked about this previously as well in a Kahoot, where we had the same sort of question about, is it more unusual to get 2 out of 3 heads, 2 out of 20 out of 30 heads, or 200 out of 300 heads? So let's change our number of coins here to 1,000. So we now have, we're flipping 1,000 coins, a ton. Remember, before we were going from about 0.35 to 0.65. Look, it's already centered it so that 0.35 is not even a possibility. And now I can see we have a spread that's about 0.44 to 0.56. So way tighter than we had previously. So that's what's coming up on our next page. Turns out we can actually find this mean and standard deviation, just like we had before, right? When we were talking about a number, our mean for a number was n times p. And I know someone had asked in class previously, why does it have that little x as a subscript on the formula sheet? And this is because it's the mean for a number versus a mean for a sample proportion. And oops, I keep doing that. My standard deviation for a number was square root of npq, which actually, as your n got bigger for both of these, it increased both the mean and the standard deviation. Whereas here, as our n increases, look, nothing to change here. My mean is still going to be at p, but my standard deviation, since my n is something in the denominator, it's actually going to go down as my n increases. And that's what we leverage to do a lot of the inference later in this class.